Let's think about arc length from a parametric curve point of view. First, let's look at if we have a table of data like this artificial airplane data. What would you say is the segment length from the first row here to the second row here? We kind of talked about it in a previous video, so go ahead and use that knowledge to write down what the segment length is here from time 3 to time 8. Well, you probably said it's square root of delta x squared plus delta y squared, which in this case is what? 7 minus 4 squared plus 22 minus 20 squared, which turns out to be basically 3.61 for this row. If you do it again here, you end up getting exactly 5, kind of interesting, because it's 4 change here and a 3 change here, and that's a 3, 4, 5 right triangle. And then let's tally up the length so far. We could say the length by time 3, starting at time 3, well, you haven't had any time to go anywhere, so your length so far is 0. Your length so far by time 8 would be the amount of time so far, the length so far from the previous row, plus the 3.61. So that would be the 3.61. I'm rounding the 3, it's like 3.60555, blah, blah, blah. But that's not the main point here. And then the length so far by the next time point, by time point 13, would be this 3.61 plus this 5 right here, which would be a total of 8.61. So that's telling us the length so far as a function we could even plot, like how far has this thing gone by time 3, by time 8, by time 13. So that's a nice way to think of it. We can also say that this value is our total length. Is there another way to see what the total length is? Well, it's just what you would get if you add up everything in this column, not this column, but add up everything in this column. So if we did a big old plus here, we'd get a total length of 3.61 plus 5, which is 8.61, which matches this. This is kind of the way we usually think about it, like an integral from a to b. This is more like the integral from a to capital T, and we keep increasing capital T, and we see the length so far is kind of a continuously evolving function. So that's a nice way to think of the arc length from a data set or a spreadsheet point of view. Let's think about it from a formula-based point of view. What are the ways we can think about total length? Well, there's two good ways to think about it. One, we could think about it as, you might have heard the formula, distance equals rate times time for motion problems. Rate would be like the speed. So we could say, what's the speed at time t times how long do I spend going that speed, and add that all up. That's a good way to think of it. Another way to think of it is just adding up these segment lengths so far. Is there a relationship between those? Well, we can say that the speed at time t is the segment length, like how far did you go, divided by how long did it take you, which is delta t. And so we see if we multiply speed at time t by delta t, we're just canceling the delta t and we're getting just total segment length. So that's a good way to think of it. We're just adding these things up. If we did that with really small delta t's, then we would call them dt's, and we would say t equals some start value to some end value. And what's our formula for speed? Go ahead and try to remember that. It was x prime of t squared plus y prime of t squared, and then times dt, just like times the delta t there. So that's our formula for arc length of a parametric curve. From a formula-based point of view. how can we relate that to what we've already seen as the arc length of a curve way back in chapter 7.4 it was? Try to remember that formula. I would have a hard time remembering it if I wasn't teaching the course. It goes like this: from x equals a to x equals b, square root 1 plus f prime of x squared dx. They seem to have mostly the same form, but there's like a 1 here and there isn't there. It's something more complicated. So let's try to establish an analogy between these, or a relationship. We're seeing a 1 here where we saw x prime squared here. So what we're seeing is that x prime of t squared equals 1, which we could as well say just x prime equals 1. I mean, it could be -1, but let's ignore that fact for now. And if x prime equals 1, what does that mean for x of t? Let's kind of take the antiderivative here. That would just be t, right? Because the derivative of t is 1. So taking the antiderivative, we get that. We get a plus c as well, but let's ignore that. So this is saying that our traditional arc length formula based on non-parametric formulas is basically our parametric formula, but just letting x of t equal t. So we can diagram it here. We had x going from a to b, and we might have something like this, and this was f of x. This is the chapter 7.4 point of view. And then here in our chapter 9.3 point of view, we're starting here, we're stopping here, and this is the x-axis, but it's kind of x of t, and we'd be doing the same thing, and this curve would be x of t, y of t, but with x of t just being t. So it's parameterizing, but letting the x value just be exactly the same as t, which is how we would get back to this situation.